Welcome back to Paranormal. This begins our series. We're actually going to have a series here on Paranormal on quantum physics and metaphysics. Now, as you can imagine, if you're interested in paranormal kinds of stuff, parapsychology, spirituality, metaphysics, and theology, and those are all terms that overlap in some way, but they are not synonymous. If you sort of traffic in any of those worlds or more than one, you have run into quantum physics ideas applied to any of those things, religion, spirituality, metaphysics, all that sort of stuff. And of course, you get drawn into discussions about the spiritual world. Is the spiritual world really kind of a useless term because everything is one and everything's a material world because of quantum physics and all that? So we run into this often enough. And there are subjects that in the lifetime of this podcast we either have touched on or will, that I thought it was a good idea to have a series on quantum physics. And really, the whole goal here is, what can we actually say accurately about these other areas? Again, what kind of theological conclusions, what kind of metaphysical statements, what kind of parapsychological assertions really are worthwhile making? In other words, really stand up under scrutiny. What kind of statements are really in concert and consistent with and legitimate to attach to the findings of quantum physics? Now, none of us are quantum physicists, and so we've invited a real live quantum physics PhD to the podcast. And again, this is a series. This will be part one of our quantum physics and metaphysics series. And so we'll introduce him in a moment, but for the sake of our listeners, I think everybody's here today. Trey Strickland is with us. Doug Overmeyer is with us. Brian Godawa. Natalina Haudeschel is with us. Doug Van Dorn. I'm Mike Heiser. And so we're all together because this is an important topic. We're glad it worked out so that everybody could be here. We all have questions to ask our guest. And our guest is, I guess we can say, Dr. Putty Putnam, because you do have a PhD. But Putty, if you could introduce yourself to the audience, sort of establish a little bit of quantum physics credibility here, and then we will jump into our topic.
Yeah, I'd love to. As you mentioned, I usually go by Putty. Technically, I'm Rob Putman, but everybody knows me as Putty. And I am presently a pastor, actually, at a Vineyard Church in Urbana-Champaign, which is in central Illinois. And so I have the kind of unique perspective of someone who has been in the theoretical physics world, specifically quantum physics, but also understands things from a pastoral angle as well. Just a touch of my story. I do indeed have a PhD in theoretical quantum physics. I got it from University of Illinois here in Urbana-Champaign, which is one of the top theoretical physics schools in the country, really in the world. It was a wonderful opportunity that I had studying there. I studied quantum field theory, and specifically for interested listeners who this may mean something, I was working on tackling some issues in quantum chromodynamics, QCD. My PhD was titled Collinear Divergences and Factorization in Perturbative QCD. And so if you have ever done any theory or experiments, it winds up being very relevant at these big particle colliders where they're, the new one they built in Europe, or before that it was over in Fermilab near Chicago, where they're crashing protons into each other at basically the speed of light and trying to sort out how to make sense of all the mess that comes out. Loved my time in the field, interacted with it a lot, participated, presented my research at Fermilab, a number of different universities and places around the globe. I really enjoyed my time in the field. I was actually awarded some departmental, both teaching and research awards. And so I say all of that to say that I became a pastor because God called me, not because I couldn't cut it in physics. I actually was definitely on the track to a good career in physics. I was enjoying it and was building a pretty good reputation in the community. But sometimes God intervenes, and that was my case. And so now I'm teaching at a town where there are a number of university students that are taking engineering and so forth, and I get to pastor a bunch of engineers understanding their world from the inside, which is pretty neat.
Yeah, yeah, and I would say, people with backgrounds like yours, and I would say just diverse backgrounds. I mean, that's really important, I think, for pastoral ministry. But that would get me on a hobby horse that we don't really have time for, or isn't relevant today. But Bible geeks like me, in church work, that can really devolve into a very insular community. So I think there's real advantage to having somebody, in the business world, the science world, whatever, get called into the ministry. I mean, God obviously, does that, and I think when He does do it, it really has the potential for some real serious payoff in people's lives, especially in the kind of the intellectual climate of today.
Mm.
So what we want to do is we want to sort of turn you loose a little bit, in giving our audience the layman's abbreviated version of how quantum mechanics, quantum physics was sort of birthed or came about or discovered, probably a better word. Sort of the background to it. So we're going to get a little bit of a history lesson here leading up to the kind of discoveries that are part of the discussion of the quantum physics world. And then we will take that information and veer off into some metaphysical stuff that we hear, and ask essentially Putty to evaluate, what are some of the ideas that sort of spring out of this pool of knowledge, this physics knowledge, and are these ideas, these assertions legit? What can we discard? What is misguided? And what's worth keeping and thinking about? And how does that help us understand, God, understand the other side? Because, we're all Christians here. And it's a very common thing in not only in Christian theology, but hey, guess what? In the New Testament, to use natural revelation, okay, what theologians would call general revelation, the created world, the natural world, as an analogy to understanding the Creator. And so we want to know what's legit there and what isn't. So Putty, why don't you just sort of jump in here and give us a bit of a backgrounding lesson on, what this thing is, quantum physics.
Yeah, I would love to. Quantum mechanics is interesting, as you've noted. It's kind of one of the popular hobby horses of the day for a lot of people, and so I think it's important, just as we talk about this, for people to understand a little bit of what it is, the history, and so forth. What are we actually talking about when we're talking about quantum mechanics? So the term quantum mechanics refers to a scientific framework, and that scientific framework is used to describe kind of a certain realm of understanding, of experiment, and usually it's applicable and necessary when we're starting to look at the world of the very small, when we're getting down to the scale of individual atoms, or below the scale of individual atoms, particles within atoms and so forth. We're in the area where, to understand the world, we need the tools of quantum mechanics. It developed basically over the course of the 20th century, and it was a revolutionary picture that just absolutely changed the way people thought about science, thought about the world of the atom. And of course, when you're talking about the fundamental building blocks of, in theory, everything, and you discover that whole thing works very different than you anticipated, then you tend to open up a lot of metaphysical questions. So the theory developed in a sequence of waves, so to speak, and I use that term sort of ironically, given we're going to be talking about waves as we go.
Nice pun there.
Yeah. My father is a literature person, so I'm versed in the pun. The first wave began essentially in the early 1900s, and the principal finding was that light is itself quantized. So this is actually interesting. It goes way back to the very beginning of physics. There was this whole discussion back and forth. Is light a wave, or is light kind of a stream of particles? And most people settled early on that light was a wave. It wasn't a stream of particles. So it's sort of more like, the waves in the ocean than it is a bunch of tiny marbles flying around. And there are waves, and particles tend to behave very differently. And so there were a bunch of experiments. They showed light behaves like a wave. But what began to happen in the early 1900s is there were a set of experiments where the only way to make sense of them was to see light not as a wave, but as a particle. There's something called black body radiation, which is essentially like when you heat something up, the way it glows, some of the study of that phenomenon. And then this other thing called the photoelectric effect, where if you shine light on a metal, sometimes it kicks off electrons. And they did studies of both of these phenomena, and they found out the only way that you can really make sense of it is if light is actually coming in these little packets that were called photons. Light is indeed a particle, not a wave. And that was just changed everything. Nobody expected that. I mean, the last person who really thought light could be a particle was basically Newton in like the 1600s. And so everybody's like, well, we have all these experiments that prove it's a wave. What does this mean? And so all of this is happening in the early 1900s. And what winds up happening is a physicist named Niels Bohr takes all of this and he proposes what's called the Bohr model of an atom. And the Bohr model of an atom is basically very simple. It basically says this. It says, look, an atom is sort of like a little solar system. You've got a nucleus in the middle that's like the sun, and your electrons are orbiting on the outside. But the trick is, unlike the solar system, where you could really have electrons, or you could have planets sort of at any distance out from the sun, electrons can't do that. They can only have a few specified paths. There's path 1, path 2, path 3, and nothing in between. And he said that basically what's happening is when an electron jumps from path 1 to path 2, it winds up spitting out a photon. Or when it jumps from 2 to 3, it spits out a photon. Or 1 to 3, it spits out a photon. But he said that can help us understand why we're getting these little packets of light, why they behave sort of the way they do. And it opened up this whole field of what was called quantum mechanics. Quantum refers to quantized, which means discrete. It means countable, essentially. And so light is countable. You can count photons. So that was kind of the first wave. The second wave then was a fleshing out of the theory that happened in the 1920s. And it began when they did an interesting experiment. And they said, well, hold on. If light, which behaves like a wave most of the time, can sometimes look like a particle, what if the particles that we're used to can also sometimes behave as a wave? And so they took electrons, which everybody believed were particles. Nobody thought those were waves. And they devised an experiment in which electrons started to look like waves. And then everybody got confused. Everybody's like, wait, hold on. So is everything sort of a wave and sort of a particle at the same time? We don't understand. How does this work? And so this opens a whole bunch of questions up, but it interestingly leads to some understanding that helps us understand why Bohr's model of the atom works the way that it does. He essentially, the physicist who did this, de Broglie, essentially argued that the reason you can only have certain orbits was because it has to be a certain number of waves. You can't have 2.5 waves. You have to have 2 waves or 3 waves or 4 waves as it orbits around the nucleus. And that kind of gives you your discrete things. And he crunched some numbers and it mostly works out. And so it's like, oh, something's happening here. Meanwhile, these two physicists called Heisenberg, who you may have heard of from the Heisenberg uncertainty principle, and Erwin Schrödinger, which you may have heard of from Schrödinger's cat, develop some pictures of quantum mechanics that give us some teeth to calculate with. They start developing some mathematical formalism that helps us solve kind of general quantum mechanics problems, which this is a big development because up until this point, we're just sort of postulating like we have these weird experiments. We don't know why it's working. These guys develop a general framework that helps us understand any given problem. Here's how you can calculate with it. Here's how you can describe it quantum mechanically once you sort of understand the problem you're working within. And that winds up being a big deal. it winds up being very effective, but also really hard to interpret. It's confusing because the mathematics is very, very strange. It works, but nobody really knows how to make sense of it. And so all kinds of sort of discussion starts popping up. How much do these correspond to physical realities or not? We don't understand. And the discussion begins to get metaphysical. And this is where the metaphysical things start kind of introducing their way and marching alongside quantum theory. We have the uncertainty principle coming in here, which basically says you can't know something's position and its momentum, which is kind of its direction, more or less, simplified its direction. You can't know them both at the same time, which essentially comes from the idea that something can be acting as a particle or a wave, but they don't act as particles or waves simultaneously. When you treat it like a particle, you have to give up the wave picture. When you treat it like a wave, you have to give up the particle picture. And that's actually where the uncertainty principle comes from. Wave 3 then develops in the 1940s and 50s, and it's where the theory is then taken to what the field would call quantum field theory. And quantum field theory is where you take all these quantum mechanical ideas and you say, okay, now let's try and figure out how the real world works. Up until that, you're sort of setting up these toy models. You're saying, well, let's pretend there's a quantum mechanical, mass on a spring, or let's look at one atom in its individuality, pretending there's nothing else in the universe. But in quantum field theory, you say, okay, let's try and look at the real world where atoms are floating around and photons are moving from one to another, and all of this. Let's solve that. And it gets really complicated, really, really complicated. But it is a aesthetically beautiful theory when you work it out. What you wind up doing is you basically have an infinite number of quantum mechanical problems that exist at every point in space, and they all talk to each other. And so it's this, like, you're pushing the edge of mathematics, you're pushing the edge of mental conceptualization, but the level of precision in the theory that gets developed is absolutely mind-blowing. There's a theory called quantum electrodynamics that comes out here, which is basically like the quantum mechanics of the electromagnetic theory, quantum mechanics of light, more or less. And the predictions that come out of quantum electrodynamics match theory and experiment to like 10 parts in a billion, or sometimes like 10 to the 12, which these numbers are like mind-blowing. It's kind of the equivalent of measuring the width of the Atlantic Ocean to the precision of a human hair. And we have like agreement between theory and experiment that's that incredible. So there's like essentially no other scientific theory that has anywhere near as precise calculational mechanisms and theory and agreement with these experiments. And so what winds up happening is a bunch of interesting things sort of come out of this development. Number one, particles develop very oddly. What's discovered is that everything is kind of a particle and a wave. And when you are trying to find a particle, it looks like a particle. But in between the time that you look at the particle, it starts kind of fuzzing out and acting like a wave where, like, for example, if I say this electron is starting at A and it's ending at B, to go from A to B in, our world, you would take one path. In the quantum world, you take every possible path. Every single possible path all together simultaneously. The electron goes through all of them. Not one of them, not two of them, all of them. And so you sort of get into the space where you're like, I don't even know what to think about that. Like, I don't even know how to mentally construct that. Antimatter is introduced here. So if you've watched, Star Trek and you're familiar with that, that kind of is a corollary of this and has indeed been discovered and experimentally verified. And you sort of get this idea that you sometimes hear referred to, which is that like the vacuum, empty space is this chaotic sea of quantum activity. Things are constantly sort of appearing in and out of existence. Anything that can happen is happening. It's this like just absolute craziness. So that's the 1940s and 50s, quantum field theory. Then from there, that technology gets applied in the 60s and 70s into the development of what's called the Standard Model. Standard Model is the description of the strong and weak and electromagnetic forces all together. It's the quantum story of basically three of the four forces in the universe. The four forces in the universe that physicists always quote: number one, gravity, which we're all familiar with; number two, electromagnetism, which is electricity, light, etc. But then there's two nuclear forces: one that holds all those protons together because they would repel each other since they're all positively charged. That's called the strong nuclear force. And the one that's involved with some radioactive decay, called the weak nuclear force. That's what actually keeps the sun burning and prevents it from just exploding in one big flaming fireball. And so the latter three of those four are all described in what's called the standard model, and it describes a whole lot of particle physics. It's the reason we built these big things like the Large Hadron Collider in Europe, Fermilab, and so forth and so on. And one of the key things that's two key findings from that: number one, something really interesting happens in that what's discovered is the electromagnetic force and that weak nuclear force are actually two sides of the same coin that you couldn't see earlier. They looked very different, but when you sort of go up to high enough energies, you find out that they're actually the same. They're actually the same mechanism that's kind of breaking down into two different mechanisms. And that winds up kind of introducing an idea where people go, oh my goodness, hold on. Maybe all of this is like one thing that's breaking down into all these different sub pieces. And so you have this idea of, maybe there's one unified theory that can describe everything. And so this kind of general direction of, all the universe is one and so forth, there's some hints that point people in that direction. There's no real evidence for much of that, and we can talk about that as we go. But it's a kind of an aesthetic idea that scientists really like. Scientists are very motivated by aesthetic. There has been a bunch of experimental confirmation of that electroweak, is what it's called. Electroweak symmetry breaking it's been confirmed. There have been Nobel Prizes handed out. That's a real thing. The other thing that comes out of the standard model is the awareness that we don't know how to put gravity in this. Every way you try, everything breaks. Everything breaks, and it's just absolutely unclear what to do. And so that brings the last wave, which is the superstring theory, which happens in the 1980s onward, and that's an attempt to try and bring gravity into the picture. And the basic idea is you take the little particles and you say, well, what if they're really, really small strings of something instead of an actual like points? It's some kind of a string. Maybe it's a loop. Maybe it's just like, a small piece that looks like a piece of yarn. What if that's the case? And so theorists get to work. They start cranking out and calculating, and it winds up solving some problems and introducing a lot of other problems. Some of the ideas that pop up, there's required extra dimensions. If you want to live in a superstring world, you have to have at least 10 dimensions. And so you kind of curl 6 of them up and you hide them, and you've got 3 of them in space and 1 of them in time, and you do things like that. There's all kinds of questions that arise. And basically, the biggest thing when it comes to superstring theory is, while there's interesting ideas here, it is absolutely unclear how on earth we ever could experimentally verify any of this. Because the scale of those little strings is so much smaller than anywhere that we can ever expect to get to. We don't know if we'll ever actually be able to test that as any kind of an actual science. And so you're sort of in the area of mathematical philosophy or something like that. But it's something where if it's not really connected to experiments, the scientific field sees it as an area of research, but not necessarily like a science, so to speak. And so that's kind of a quick overview of the development over the last 100 years, some of the key ideas. I'm sure that has introduced a bunch of different things. I can summarize some of the key findings if that'd be helpful, or if you guys want to jump into questions, I'm open. Whatever you want to do.
Well, that was a better summary than like 50 YouTube videos I tried watching. So.
Yeah, I have a couple things that I'll just throw out, and for the sake of the listener, we're going to post a couple YouTube videos or links to them along with the episodes so that you can get a little bit of a feel for some of what, Putty just summarized as far as, major ideas and experiments that led to this or that idea. So if you don't have any background in this, you can go up and watch that. But you said, I'm going to pull out two things that you said, and again, that we've all seen in videos or maybe read elsewhere too. You said something to the effect of particles behave very oddly. So they have this, they can both be waves, and they can be waves as well as be particles. They wander around like waves until you check up on them, until you observe them. And there's actually, one of the videos I watched sort of made this hit home for me, that particles or light, behaves one way until you watch what it's doing, and then it does something that's different. And so that gives rise to a question like, is this material stuff, is light conscious? Okay. And then the other thing, you mentioned that particles are constantly vanishing or going in and out of existence. So that raises the question, how does this jive with matter can neither be created nor destroyed? So,
right.
I mean, is this chaos? Is this order? Is it a little bit of both? But you mix this, if it can't be created or destroyed, then it's just always been here. And so that takes you into a metaphysical place.
Sure.
If particles behave like that in a way that looks like consciousness, is that the case? Like, do we have this? I think the modern term now is biocosm. That the universe is sort of this living entity that's always here. Using language like that to describe the universe itself, it had no beginning, it has no end, because these are very metaphysical, kinds of things. And for this episode, we all read an article from a theology journal that essentially you could boil it down to, quantum physics raises some potentially disturbing questions. and then the other one by a guy named Stenger was really, really down. I mean, negative about these metaphysical statements that people make. And just I'll pull one observation from his article. Again, we'll post references to these. But here's his sentence, that the quantum metaphysics, quote, exploits the strong role of the observer. That's almost another way of saying that we're all getting hoodwinked by this metaphysics talk, that we shouldn't even be talking about these things the way we're talking about them, because it's kind of like we're like in a position, well, we can't really think of any other way to talk about them, so let's talk about them this way.
Right.
And then that leads to theological and religious conclusions. So how do we sort all this out?
Right. So can you just succinctly state both of those questions again?
Yeah, you had particles behave very oddly. They look like they're conscious.
Right.
So what's up with that? And then particles constantly vanishing in and out of existence. Okay, how does that jive with matter can't be either created or destroyed? In other words, is it eternal? So do we have an eternal conscious thing in the universe? Are these ideas that can be rightly abstracted or asserted on the basis of quantum physics?
Right. So, you mentioned the way that the scientific community views a lot of this metaphysics. And my experience with that was essentially this, that, for some reason, perhaps with all of us, but at least with some set of human beings, there's this kind of desire to live in a fascinating, exciting world or something like that. And so I think because of that, there's sort of a tendency to layer the most bizarre and the most extreme understandings possible on top of certain events or facts or whatever. And I think because of that tendency, there have always been some subset of people that look at quantum mechanics and develop these very metaphysical explanations of it. For example, there's books that are written by scientists that push in this direction. There's a book called The Tao of Physics, I think it is. And there's another one, Dancing Woolly Masters, which is, they're basically books on Eastern philosophy where they're saying, look, quantum mechanics sort of looks like Eastern philosophy, so therefore it's a proof of it. And what the majority of the scientific community thinks and believes, from what I understand, is that, the purpose of a scientific paradigm is to allow a way to explain and predict data. At times, those paradigms allow us to make broader statements about the way the world may work, or what truth is or isn't, or so forth. But I don't know that that's necessarily a requirement that needs to be put upon a scientific theory. Kind of the core presupposition of science is we are going to do experiments and we are going to develop theories that concretely help us describe these experiments. And if it can't be reproduced in another experiment and we can't describe it, then we're not going to call it science. We're going to call it philosophy or metaphysics or something else. And I think when we take the ideas of quantum mechanics, which work very well as a descriptive calculational framework, but when we take those ideas and we layer upon them understandings of, therefore, this is how the universe works, or ... we are theorizing upon a theory, if that makes sense. Like, quantum theory is established as a calculational framework. It does not need metaphysical ideas. But when we take that calculational framework and then we say, now let's theorize about this theory, then we're stepping into the area of metaphysics. And so the vast majority of the scientific community really rolls their eyes at this kind of stuff. And they say, this is not science. Let's not call this science. That's really kind of silly. Yes, it's true that looking at this theory, it doesn't rule out Eastern mysticism, or it doesn't rule out this kind of thing. But that's really an argument from silence. That's saying, well, it's not incompatible, therefore it's compatible. Or therefore it's a proof or something. And most of us feel that that's far too strong. And so, taking all of that and circling back to your comment, it looks like the light has consciousness, or it looks like it knows when it's being looked at, or whatever. If you want to anthropomorphize it, sure, it does look like that, right? It looks like it's aware that it's being watched. But if you begin to think a little more carefully, I'm not sure that really makes a lot of sense. Because, when we do these experiments, the way we describe them, we always kind of describe it as if somebody is actually sitting there with their eyeballs looking to see what the photon is doing, or the electron, or whatever. But that's not what's happening. What's happening is we're doing some experiment that is being picked up by some kind of sensor or detector, which is getting logged in some kind of a computer. If you look at these particle colliders that are happening, nowadays over in Europe, it's constantly logging data that's getting saved over on hard drives that years later is getting pulled out and examined. And so, this idea that it's like your consciousness interacts with the quantum stuff isn't what's happening there. Like, a computer is interacting with it, like a hard drive is recording it. And then years later, our consciousness is interacting with that data. And so when we're talking about observation, I think it's important that we don't personalize that too much. The quantum mechanical world is weird. These things behave very oddly. It's very strange. It's not the rules of the world that we would expect they would be. But just because it's weird doesn't mean that it's conscious, or that it's, some of these other facets. A lot of the weirdness in quantum mechanics, here's a question you have to ask yourself as a scientist. Why didn't we discover all of this a long time ago? Why is this so shocking? Science had been around for 300 years before quantum mechanics shows up. So if this is the way things really work, this is the core truth of the universe or whatever, why did it take us 300 years to find it? And why does it look so very different than everything else we found so far? And the answer is that quantum mechanics fuzzes out very quickly once you take a small step back from the atom. Once you're not looking at individual atoms, but once you're looking even at molecules or collections of molecules, 99.9999% of the evidence of quantum mechanics like just completely disappears. And other rules are what describe things more effectively. And so, when we talk about observation, what we have to realize is anytime we're introducing something quantum mechanical into an observation device, we are making it cross that horizon outside of the realm where quantum mechanics effectively describes things. Every detector is some big thing that is way bigger than quantum mechanical scales. And so, most of the way that the scientific theory, for example, or the scientific community would interpret things like that is we say, well, we're introducing what's called decoherence in the quantum mechanics by introducing it to a detector. And when that happens, the quantum mechanical effects fuzz out and it starts looking like a particle instead of a wave. I even had a professor do a lecture on exactly that in my Quantum 2 course in the University of Illinois. And so, we can layer these things on top of quantum mechanics, but it's not really contained within the science. It's not really contained within the physics. Now, to the idea of can matter be created or destroyed and how does all of that work? It turns out that matter can indeed actually be created and destroyed. And that is sort of the core presupposition of Einstein's famous E equals mc squared. That's a description saying apparently matter and energy are more interchangeable than we had realized. And so atomic energy, whether destructive or constructive, is all essentially working on that conversion. It's taking some amount of atomic matter and converting it to energy. It is the case that seems sort of shocking, but this idea that matter can't be created or destroyed, that's a postulate. That was kind of like an idea that was just put out there as a scientific, we think we'll use this. We'll take this and see how far we can run with it. And it worked really well until you get to quantum mechanics. And then it doesn't work so well in quantum mechanics. But I'm not sure that means there's some fundamental problem with the universe. It just means you didn't guess quite right, if that makes sense.
What about, again, I need a simple analogy. And as I'm listening to you, I'm thinking, okay, it seems to me like on this consciousness question that we are confusing an observation. In other words, we observe a behavior and then we presume to know why the behavior happens. I can be watching my kid, okay, and my kid does a certain thing, like picks up an object, and it may be something that I don't want them to see, okay, something like a bill, okay. And, I can look at the behavior, and that's one thing, but how in the world could I correctly understand why he picked up that thing and what led to the picking up of that thing and what's going through his head when he looks at that thing? So those are entirely different things. And as an observer, I can only see the behavior. But it seems like the metaphysics ideas really take the reality of seeing the behavior and then presume certain things that become I'll make a pun of my own here, but just become gospel, become metaphysical gospel, when there's really no way to know, does that particle have consciousness? If it did, is it making a decision? Well, it would have to be making a decision if it has consciousness. And we could think, for hours about the decisions that are going on inside the particle's little head, as it were. But we wouldn't be any more correct about that than what's going on inside the teenager's head. Mm-hmm. In other words, there seems to be a real disconnect here to me. So is that what you're getting at, that this confusion between observation and our interpretation of the observation? In other words, we're the problem. The problem isn't the particle. The particle does what it does,
right?
Not, but we are building a metaphysical system not based on the particle, but based upon our imaginations about the particle.
Yeah, no, I mean, I think that's a pretty good description. As I said, quantum mechanics, it's a calculational framework. It's a set of rules. It says, set it up this way, turn this crank, and you're going to get the numbers that you can measure in your detector, right? That set of rules, they're expressed in equations, right? And equations don't really usually have a lot of metaphysical interpretation to them, if that makes sense. Like they're mathematical, and so when we start layering metaphysics on top of the science, that's exactly what we're doing. We're putting it on top of science. It's not the science itself. It might sort of quote unquote feel the same, which is what is essentially the connection that most people who are going in this direction draw. Like, oh, this feels like this metaphysics, so it's a proof that this is like that. But as a scientist, one of the things that's important, in my opinion, for us to keep in the back of our mind is there's a difference between a scientific model and reality, right? A scientific model is a conceptual framework that's trying to describe reality in some way, but that's different from what reality is. And as we've done science, our models have changed. Once upon a time, Newton was setting the models, and the world looked and felt like a very different place. Well, now quantum mechanics is setting some set of models, and the world looks and feels more mysterious. Has the world changed? No, of course not. But our models have changed. And in my opinion, I think we're a little presumptuous to think that just because we have a set of models now, that we're accurately able to describe the true nature of reality. Generally, the way physics has worked is that every window that we've opened up has introduced a whole new room that we had no idea existed in the universe. And we're like, oh my goodness, this is shocking. The world is so different than what we thought. And that's happened over and over and over and over and over again, and continues to happen. And so it's really unclear to me why we would say, take the current understanding and say, we understand everything now. Like, this is how the universe works. There's nothing left to discover. This is a complete set of rules or laws. Everything in the history of science would say that can't possibly be true. And so I think there's a bunch of layers that are happening there. Like, I distrust that from a historical point of view. I distrust that from a scientific point of view. I'm not really trained as a philosopher, but even philosophically, that sort of feels odd to me, that we would take these formulas and jump to a metaphysical understanding when those very, very same formulas, for example, don't describe a lot of other things well. They don't describe how, you and I, our relationship works, and that's part of reality. They don't describe the way I interact with my family. They don't describe the way I drive my car to work. They don't describe any of those things. And yet we sort of isolate them and say, these are the true rules of reality. We should build our metaphysics on this. All feels very shady to me.
It kind of reminds me in the 1700s when they discovered that lightning, they put a scientific framework to understand lightning, and how theologians were saying, no, that's the act of God, and if you apply science to that, you're gonna take one of God's tools away. Like, well, no, not really. Like, you're applying a metaphysical framework onto your bad science. And now that science can describe what lightning is, has nothing to do with God. It's just how the world works. And so when I was, reading some of these articles and watching some of the metaphysical explanations, of, if you observe a particle, it does such and such, or you rotate this particle and then that particle over there does the same thing. Therefore, it's all is one, and we're all part of some cosmic consciousness. Like, well, the therefore is not implicit in the science. Like,
exactly.
Let's just wait another 100 years before you add the therefore.
Well, and even like, if I was going to even just not take that metaphysically, right? If I was just going to even say, look, every particle, between where it leaves and where it arrives, fuzzes out and takes every possible path. Like, that's a clear, well-defined statement in quantum mechanics, right? And is true on the quantum mechanical scale. But even if I just take that idea, I can't even apply that idea to throwing a baseball, which is you're even setting up the same problem just on a different scale, and that therefore doesn't work. So
does that mean you're referring to the difference between the physics on a quantum level are different than the physics on a classical or larger scale, like that, like they haven't been able to unite those two yet? Is that what you're referring to?
Yeah, I mean, that's a slightly yes and no. I'll put it that way. Yes and no. That is true. The physics of the very large is best described usually by what's called general relativity, and that was one of Einstein's contributions. And the physics of the very small is generally described best by quantum mechanics, but the two of these are pretty incompatible. We don't know how to put them together. And sometimes they come together, like black holes, for example. You've got high gravity, but basically infinitesimal size, and so we don't really know what to do with that. And this is getting into that idea. But what I'm trying to basically say is this: is that every scientific model has a set of parameters of what it can accurately describe. And that's what kind of tends to get missed in this whole quantum mechanical thing. There's this idea that, like, because it's the smallest, it's the most fundamental rules of reality, so therefore it can describe everything. And what I'm saying is that's a leap in logic.
It's a quantum leap.
It's a quantum leap. It's not accurate. The rules of quantum mechanics are wonderful for where they apply, but they are not universal rules that apply in every instance and in every circumstance.
And that's really important because, in fact, this whole thing has been so interesting to me because before I became a Christian, I was really deeply involved in the New Age. And that was the first place that I started hearing these quantum physics, the whole idea of it really being talked about in a spiritual way. And I used the term when we talked just before we started recording that I'm, as a Christian, scared of quantum physics. That was the wrong word. It's more I'm hesitant because of how we applied it as New Agers. And it seems like not only is it that there's this whole idea of all is one, but it even is more drilled down to this, what Dr. Heiser was talking about, this concept of the observer changing the behavior of the particle. That is like the linchpin of so much of modern New Age philosophy, which does, interact with Eastern mysticism. There's so much of this. There's that documentary, What the Bleep Do We Know? And Down the Rabbit Hole. And that's all quantum physics related to these New Age philosophies. And the idea is that since, and this is me kind of quoting that realm and the way they apply it, but since observing these particles can change the way they behave, this must mean that I can manifest my own reality by visualization. And this is how they apply quantum physics to it. I can visualize, because I am the observer, what I want to happen in my reality. And because quantum physics has proven that I have control over the way that my world behaves, I can actually manifest all of this. It goes into the law of attraction and The Secret and all of that. They all use these quantum physics principles to back up this idea that you can bring whatever it is that you visualize into being based almost solely on that experiment of the quote unquote observer changing the behavior of the particle. And that is like what it all hinges on. I mean, you've got people like J.Z. Knight of the Ramtha School of Enlightenment saying she's a quantum physicist now, and it proves that she's been right all along. And as silly as it sounds, this is where they're seeking validation for what they've been claiming about this whole manifesting your own reality idea. And we do see it kind of crossing into Christian realms a little bit too, the visualization and making it happen and that kind of thing, the power of positive thinking. Now they say, okay, here's the science to back it up. Right. So this is really, really helpful to break it down and understand from your perspective,
Right. Right.
how that is so wrong.
Right. And the key idea is, again, here, it's, on, are we playing in the sandbox where quantum mechanics applies or not? And what I'm essentially saying is that, like, when we're beginning to talk about human beings and human being size scales, the rules of quantum mechanics are not going to be applicable to our reality. Almost all of the time, we have to work extremely hard for quantum mechanical things to show up. Like, for example, a laser is a quantum mechanical device that we can, use on. But there's an awful lot of time and energy and work that goes into massaging the exact right set of circumstances so that quantum mechanic effects don't just disappear. And I would sort of equally argue, like, well, if we're just going to kind of grab random quantum mechanical ideas, then I should be able to walk through walls, because that happens all the time quantum mechanically.
They claim you can. They claim you can
disappear from home and appear at work. All of these things can, like, if I'm going to just start grabbing those things and applying them at the personal scale, then all kinds of things sort of get real weird. And I realize that, like, some set of people will use that and say, yeah, we should be able to do that. We should be able to do that. Right. But I would just say,
well, people say, well, Jesus did, right? And when he came back, I mean, but
right.
you would say, well, that's not a quantum mechanic thing. That's something else, because the quantum mechanics breaks down at the size of an atom, let alone the size of a person.
Right. Yes.
But I've heard that, like, well, the particles pass through solid objects and they pop in and out of existence. Hey, that's right there, man. That's how you interpret, Zechariah, whatever, or right. Jesus walking through walls or whatever. And
I would say that scientifically, it would be more of a miracle to be able to get a human being into a quantum state where they could walk through a wall and rematerialize as a human being back into the person that they were before. That, to me, would be a far bigger miracle than something in the spiritual realm happening, which would be another explanation of that. Like, I'm not even sure that to put yourself in a quantum state where you could walk through a wall, you're going to disintegrate. You're going to fall apart. There's all, like, everything falls apart. Like, you just, it's a beautiful idea, just not the way that it would actually work.
I want to bring up something that might be uncomfortable here. I guess that's my job. I can't help thinking that all this quantum metaphysics talk is maybe an unconscious or conscious reaction against the earlier use of science to do theology on the part of, mainstream Christianity of centuries gone by. What I mean by that is, there would be the science of the day, and then the science of the day would be reacted to and then come out on the other end as some sort of justification for Orthodox Christian theology. In other words, Christians would parse it a certain way. And so this just seems to me to be a reaction of the same kind, but against, sort of traditional theological ideas. And so it has a little bit of a, well, if you guys can do it, we can do it too, kind of feel to it. And the reverse of that is, I think we need to realize that we quote unquote commit the same crimes, or it seems like we do, that the quantum metaphysicians do even today. Here's my example. How many times have we heard or defended ourselves the idea of intelligent design using the watch and the watchmaker thing? All the quantum people are doing is saying, I'm making this observation. I'm looking at this observation of this, particle of light. And now I'm going to take that observation, and instead of, taking the order of it and coming out with a watchmaker, I'm taking the disorder of it and coming out with, randomness or all is one or something like that. They're doing the same thing. And I think we need to own that we sort of gave birth to this method of what they're doing. And at the same time, we need to realize that just as the anti-intelligent design crowd today will say, yeah, you're looking at a watch, but that's your observation. But the extrapolations you're making from the watch to argue for a designer are just as illegitimate as what the quantum people are doing, taking their observations about particle behavior and then making their own theological conclusions. So having said all that, is that an appropriate critical analogy? Why can we do it to come out with intelligent design, but then we spank the quantum metaphysicians for using the same method?
I think that's a question worth posing. And I've had people tell me for a long, long time, "Oh, Putty, you need to write a book about how, quantum physics points towards God, et cetera, et cetera." And I lean away from that for the same reasons that I'm saying I'm not sure that I like doing that in a new age direction or whatever as well. If I'm gonna wear my pastor hat along with my science hat for a moment here, Scripture is pretty clear that the revelation of God is found in Jesus Christ, right? And I think, in my opinion, there are things that we can learn and enjoy from the study of the natural sciences. But what we wind up doing, without necessarily even realizing we're doing it, is we sort of begin to create like typology type analogies, like, oh, nature acts this way, therefore, this is true or that is true or whatever. And, from what I can see in the Scripture, like, there's definitely typology in the Scripture, but typology is always run through Jesus Christ. It's never typology independent of the revelation that's given through Jesus Christ. And so to me, like, the only way that's fair from a Christian and a biblical point of view is to hold on to both of those, if that makes sense. And to say, like, this is who Jesus reveals that the universe is like, or reveals who God is. And, oh, that God also made the universe, and here's a few of his fingerprints. But to kind of try to run it the other way and to say, well, here are some fingerprints, therefore God is like this, puts you in real dangerous territory, which is essentially what you're saying. And I agree. I largely agree with that assessment.
Yeah, it's one of the reasons. I mean, it's certainly not the only reason why I today, shy away from making Scripture speak to questions that it never asks. This whole thing about the Bible being a science book, something that teaches science. I mean, if we're going to look at it for what it is, again, just let the Bible be what it is. That seems to be a pretty simple axiomatic idea. Let it be what it is. And what it is a thing that was produced in the second millennium BC by people who didn't know any of this, didn't know about germs, they didn't know, any number of things about science. And God knew that because he's God, but he picked them anyway. And that should tell us that he had a different reason for picking them. He had something different for them to communicate that they were perfectly capable of pulling off. They didn't need scientific knowledge, and he didn't need to give them scientific knowledge to do it. And if he had, it would be incomprehensible to anyone else but them, which sort of undermines the whole communication idea. I mean, all these things float around in my head, but that they're not popular in Christian circles because we've sort of trained ourselves to use science to justify the Bible, and then we turn around and say the Bible teaches this thing that we've just used to justify it. And I see it as very tenuous methodology that's easy to dissect and dismantle, and it's all unnecessary. So I would agree with your assessment that why can't we just hold both of these things, one in each hand, and affirm them both, rather than making one, rather than trying to come up with some cause and effect relationship that works both ways and every way. I just don't see the necessity for that.
You mean there's a group of people who say, well, quantum physics verifies the Hindu Vedas, and other people say, well, no, quantum physics explains the prophecies in Isaiah,
Yeah.
or the miracles of Jesus. Like, I think that's
none of that seems legitimate to me.
Yeah, I mean, I don't think that Jeremiah was writing to a people and thought, well, no one will understand this until they discover this mathematical model of the super small.
And people will say, well, then you're saying that the Bible contradicts, or science contradicts the Bible, and the Bible's wrong. No, I'm not saying that at all. I'm just saying that one thing doesn't produce the other.
Mm-hmm.
I'm saying I'm not omniscient to know how to marry them, or even if they need to be married. They just are. Okay, so I don't like the methodology, whether a Hindu, Eastern mystic person is doing it, or whether a fundamentalist Christian is doing it, because I just know that either of them is going to run into problems. And in many, I think what we're hearing here is they actually run into the same problems. It's just that they're trying to produce a different outcome by virtue of their method.
Mm-hmm. Yeah. No, I'm totally with you, Mike. And I mean, I think a lot of times the heart behind it is probably fairly good. It's like trying to speak the language of the day and things like that. But I think it's sloppy logically and some things. And I think it can just frankly get you into dangerous territory because, as you pointed out, once you open the door towards Christianity, well, that door can kind of lead to any philosophy you want. Who's to say that Christianity is better than Hinduism, New Age, or whatever? Yeah, I'm inclined to lean against it as a pastor and a scientist.
Yeah, see, I want to evaluate, a religious system by the coherence or incoherence of its truth claims. That, and I don't need, I don't need quantum physics to do that. If I knew quantum physics really well, maybe at some point there'd be a good illustration. And I think that, like you said, there are. You run across some of those things that might be helpful, but you have to really be guarded on, am I doing theology from my knowledge of quantum physics as though I desperately need a point of physics to be able to say this?
Mm-hmm.
Like that gives it its legitimacy. And I just think anybody who's doing that for, with any outcome in view, I think they're going to run into the same sorts of problems.
So, Putty, I have a question. As I was reading and watching a bunch of videos, going back to kind of Mike's very first point, every question that I had that I wanted to ask you was in some way or another about the idea of observation. So, as we've been talking here, it seems to me like the whole idea of observation quickly moves, and I'm talking about like the two-slit experiment that, well, when it goes through, it appears like from our observation of it. So, like, that seems to be the door that's moving from the physics to the metaphysics. So I guess the question that I want to ask right now is, how would you describe the two-slot experiment and what happens when that particle goes through the two slots in a way that isn't metaphysical? Because that's what every single person that I saw on the internet was doing.
Mm.
They were bringing it out that way. So is there a way that you would do that you could communicate it to a person that's never heard of it before that would make sense?
That's an awesome question. I love that question. Yeah, I've never thought about this, so let me kind of just shoot from the hip on it. But so okay, let's do the two-slit experiment with using electrons, because that is more demonstrably quantum mechanical. And I'll describe it. So for our listeners, I assume maybe they'll attach something on the website where you can look a little more deeply. But
yeah, we will.
The double slit experiment for electrons, essentially, what you're doing is you're taking electrons and you're kind of firing them at a little barrier that has two small holes in it. And the electrons, you don't know which hole they go through, or how exactly that works. You're not really aware of what's happening there, but somehow they're passing through that. And when they get to the screen behind those holes, they wind up landing somewhere. And over time, as you kind of measure more and more of these electrons and where they land, you get a picture that looks like the electrons are acting like waves, kind of interfering with themselves and sort of not really going through either of these holes, but kind of going through both. And basically, they sort of wave their way from the gun to the screen, where they turn into a particle again. That's kind of the outline of the experiment. And so if I was talking not metaphysically, what I would say is I would say this. Okay, so you're somehow generating electrons and you're shooting them out of your, quote, electron gun. And when the electrons exit the electron gun, they are in a state where essentially the quantum mechanical rules of the universe are a good description. So it's the right sizes, it's the right energy states, it's all of that stuff. And so between the time where it leaves your gun and it arrives on the screen behind the slits, it's living in the world of quantum mechanics. And in the world of quantum mechanics, things look like they go through every possible direction and every possible path. In fact, it looks like it waves in every possible direction, and all those waves bounce off each other and interfere with each other and all of that. But so it lives in the quantum mechanical realm. And in the quantum mechanical realm, it sort of fuzzes out. It's not clear where it is at any given time. It's not really clear which direction it's heading, because it's kind of doing all of them simultaneously. And so that sort of process of walking out all possible paths continues until the electron intersects. I should say actually the sort of fuzzed out thing that describes where the electron could be intersects the screen. Now, once it intersects the screen, we have a transition where it is now entering a place where the rules of quantum mechanics are now not a helpful description of how the universe works anymore, because it's now going to intersect a screen, which is going to force some set of atoms to collide against each other and bump up into each other, and you're starting to hit more and more things here, and then they have to start radiating light, which is crashing into each other, which is eventually getting big enough that a camera can take a picture of the light, or some sort of a detector can register, oh, it landed here, or whatever it is. And by the time we're at that point where it's observational by someone, somehow, electronically, visually, or whatever, we've crossed the barrier where quantum mechanics isn't really a good picture anymore. And it is where that quantum mechanical cloud gets forced across the barrier where quantum mechanics ain't going to help you anymore. That process takes that whole cloud and condenses it down into one place, which is where the electron registers. Now, how all of that works is some complicated rules of mathematics and so forth and so on. But that interaction isn't personal, if that makes sense. It's just you're living in a space where you have one set of rules that apply, and then you cross a boundary which introduces another set of rules which collapse the openness of the system into a closed, well-defined state. That would be how I would describe it without getting metaphysical or observational or whatever it is.
Are we just moving in? Is it, for my simple mind, is it a movement from like certainty of a thing just into probability or statistics, or is it something more than that?
Probability and statistics are definitely a big piece. And when I'm talking about the electron sort of goes everywhere, I have in mind a very specific way that probability is playing out. But yes, probability is a key in quantum mechanics. And it's one of those things that's odd. You can never really, in a quantum mechanical experiment, you can't say, I know this precisely is going to happen most of the time. What you can say is, I know if we were going to repeat this experiment 100,000 times, this would be the probability distribution we'd get.
Right.
You don't know what any given one is going to do, but you know what the statistical compilation of them will do.
I have a question. This is Gadawa. It's related to this because what you're saying reminds me of some of the things we read, and I think one of the in one of the articles, the guy explaining the wave particle duality and stuff, he was explaining the probabilism, and he mentioned how there's, and it's kind of interesting that he just said this in one little sentence, but I don't see a lot of people referencing this. But he said that there still is two different approaches to the mathematics, and that is the ontic versus the epistemic. And the ontic is that the mathematics accurately represents ontological reality, and the epistemic approach is no, we don't know what reality is because we would have to actually be godlike to know reality. So it really only describes our knowledge or our observations. It's sort of like the realism versus the non-realistic approach to science, And even I read that Hawking even claimed to be a non-realist in the sense that he said I'm more about the mathematics describing the reality than the reality itself. And so to me that actually kind of makes more gives a bit more. A bit able to explain this thing that we've been talking about, where you can't tie your theology to the science, you can't tie it to it, and why can't you? Because it's a very natural tendency. Everyone seems to be doing it, and but this thing of epistemic versus ontic seems to shed some light on that. I don't know if you could expand on that or not.
Yeah, I'm flipping through the articles here. I was hoping to be able to find that section and review it real quick. I did remember reading that.
Yes, I know where it is. I had it. It was the I lost the article. It was the one online.
I think I said
Forbes. It was the Forbes one. 6 things everyone should know about quantum.
Right.
And it's on the first page. He says, whether you consider this as the system really being in all of the states at once, or just being in one unknown state, depends largely on your feelings about ontic versus epistemic models.
Right.
Though these are both subject to constraints from the next item.
Right. Yeah. So this is very much getting into that that idea that I was describing earlier, where it's like we know the mathematical technology. That much is unambiguous, and it works really, really well. The problem is that the mathematical technology is so far removed from the kinds of things that we know how to make physical sense of that it's kind of a guess as to whether it means anything or not. And what I mean by that is this, if that seems sort of odd, right? So, at some point science, it lives in the very tangible and concrete realm. When you measure the mass of something, you're putting it on a scale and you're reading a number, and you can pick up and hold the thing and, oh, this feels heavier than that other thing. And it kind of like, touches your physical senses. And so theories that you build that use those kinds of tools, you kind of know how to make sense of. The machinery of quantum mechanics involves using mathematical tools and operators that are necessarily non-physical. So at the very least, for example, you're living in the world of imaginary numbers, where you have square roots of negative numbers floating around everywhere, which are non-physical. You are dealing with wave functions, which are sort of related to the probabilities, but not in a well-defined, clear way, because you have to take the wave function and then multiply it by what's called its complex conjugate so that it turns into a real number, not an imaginary number. And it's that squared wave function that describes your probability. But all the rules apply to the wave function, not to the squared wave function. And if you try to work with the squared wave function, it doesn't work. And so you sort of have all of these made up tools that you then have to kind of translate into physical results. And the question is sort of like, okay, so we know how to work with the made up tools, and we know how to translate them into physical results. Like, we can turn the crank, but the more we try to see if this corresponds to any physical reality, the more it seems like we can't find it if it does.
That reminds me, I used to read Michael Polanyi. He's a philosopher of science, and he would always point out that there was a famous article back in the 50s that has never been answered, and it was the the unreasonable effectiveness of mathematics in the natural world. And his whole argument was that science works in the sense that the math fits, but scientists don't know how or why it fits. It's just that it does. Like they don't know how it is that mathematics connects to the real world or the natural real world, but only that it does. And that has something to do with, maybe that's where the philosophical worldview comes in terms of how people then start to reinterpret the mathematics. I don't know.
Yeah, I mean, there's all kinds of questions. Why does mathematics describe reality? That's kind of an assumption. I mean, it's convenient, right? Yeah. But why? You left science behind when you're asking that.
Yeah.
Hey, Putty, it's Trey here. Getting back to the barrier that you're referring to at the quantum mechanics level, and it kind of crosses that barrier and enters in a kind of a fuzzy logic, and it comes back across the barrier as a particle or whatever. Is there a term for that? I mean, is that reality? What is that?
A term for what specific?
Just
part
that
of
barrier, just that whole process of it. We have mathematics that can kind of explain quantum mechanics, and then it dips down across this barrier, talking about the split experiment, and then whether that barrier is the act of observation, whatever, it crosses that barrier, and then it comes into our reality where we can then observe it as a particle or whatever. My question is, that barrier, I'm kind of stuck on that. We all kind of watched that movie. In fact, that video that I'll post up on the website that Mike sent us was actually in that movie that Natalina referenced earlier. And ever since then, I was kind of caught up in metaphysics as well, and talking about the act of observing. Is that what makes our reality? So it's kind of like if a tree falls in the wood, doesn't make a sound. If nobody's there to observe it, doesn't even exist type scenario. And I always thought about like the watchers in the Bible. I thought it was interesting that they're called watchers, and the mere act of watching us and observing us kind of creates our reality and holds matter in a physical sense, rather than us all vibrating in waves everywhere.
Yeah, so to kind of respond, I think, to your question, there's a term that gets used in the field that's called coherence and decoherence. And quantum coherence is when you're in a set of circumstances where all the kind of oddnesses of quantum mechanics are allowed to produce results that are unexpected. It's where you're in a place where the quantum mechanical rules are like kind of the well-defined rules, and you need them to really describe what's really happening. And then decoherence is when you're in a place where it's like you're not in that place where all possible states are being explored and all possible things are kind of happening concurrently, but where all of that decoheres and you're kind of isolated into a single state or a single place or a single location or whatever it is. And a lot of what I'm arguing essentially is that, when we personalize observation, we're doing something kind of silly, because physically observation should cause decoherence. And that decoherence basically washes out all the quantum mechanical effects and makes something look like it's in a specific place instead of in all places or whatever it is. And there's no need to add a personal layer to that decoherence thing. It's well defined and demonstrated physically. Like you can turn the crank on the equations and say, when I do this, it's going to decohere and all the quantum mechanical spookiness is going to disappear and it's going to be here or there. Like it's clear. And it doesn't require a person, so to speak. Observation, when we talk about observation, a lot of times what we're talking about is forcing decoherence. And when we're in a place where we're not forcing decoherence, things will tend to quantum mechanically drift around. And so the question you're always asking is, how long has it been before and after, between, what's the interval between forced decoherences? If that interval is really long, then you have quantum mechanical things tending to happen. But, when we're looking at human beings and we're looking at all those things, the interval between decoherence is basically zero. You're never wandering around in quantum mechanical states. Like, you're constantly forced into all the time decoherence. And so that's why it looks like the rules of quantum mechanics kind of wash out and basically go away. Maybe I answered your question. Not sure if I did right.
Yeah, that's good.
Anybody else have a question?
I do, but I mean, we could just keep going. But
Yeah, I got a million of them.
wait,
That's why we've got round 2 and 3, right?
That's
okay,
right.
I think this is relevant though.
Okay, go ahead.
Wave-particle duality. So this is another one of these fundamental things that keeps being referred to in everything I read and all that kind of stuff. And the analogy that I get is like, is the wave and the particle really? At what point does the measuring tool itself come into the equation? Because if I take a desk and I use two different measuring tools, I measure with a millimeter and I get whatever, 1,000 millimeters, whatever, and I measure that same desk and I get it's 50 inches. What, the desk is both 50 inches and 1,000 millimeters at the same time. It's two different things. I'm like, no, I mean, I used a different measuring tool, and the measuring tool itself actually restricts it, or let's put it this way, there are limitations and boundaries to the measuring tools itself. So the measuring tool itself actually binds our ability to observe. So it excludes some things and it includes some things. So that I guess what I'm saying is, at what point does that come into the equation of our knowledge? Because you know what I'm saying? Does that make sense?
Yeah, no, I mean, I think you're floating around the right idea. Your specific analogy is trace limited because I can convert between inches and millimeters, right? So I can demonstrate that the two of those are two equivalent descriptions of the same thing with different labels. Particles and waves aren't equivalent in that way. But your idea that, the way that I measure determines the possibilities of what I may find, is exactly the way that things are teased out in quantum mechanics. The way it often gets described, kind of wave-particle duality, I don't even necessarily love that language. That was language that came about in the very early development of quantum mechanics. And it sort of, what it does is it kind of paints this picture that these things are sort of particles and waves are mutually exclusive, and that these things are sort of both mutually exclusive things. And I think a more accurate picture would be to say that on the quantum mechanical level, there are neither particles nor waves. There are wave particles. If that makes sense. There's wave particles. There's both, but depending on how you measure, if you measure like it's a wave, you're going to see a wave. If you're going to measure like it's a particle, you're going to see a particle. And you can concoct these interesting experiments where it can look like it's acting like a wave until you force a look at it that makes it look like a particle. And that's the idea of the whole double slit experiment. Like, you have this area where it's like it's acting like a wave, and then I force it to look like a particle. And now I look really confused because, well, if it was a particle all along, it wouldn't have done this. Well, it wasn't a wave or a particle all along. It was a wave particle, and it's still a wave particle. It's just that the way you measured it, in this case, makes it look like a particle.
That's an important phrase, force a look. I mean, really, that's pretty important, because then it's all about the observer. And I think that's the point of Brian's question. It's all about the observer and the instrument, and it says nothing about the presumed consciousness of the wave particle.
Mm-hmm. I would even go one step further, and I'd say it's all about the observation, not about the observer.
Yeah.
Okay.
Well,
because it's not personal.
Is it possible to, before the thing goes into the two slits, is it possible to measure it as a wave?
That's a good question. Quite possibly. I'm not an experimental physicist, so I couldn't give you the cut and dry on that. One of the challenges, again, the way they depict these on the PBS specials and whatever is often far from reality, because
no.
the
The metaphysics.
just like biblical studies.
Right.
Ancient alien quantum physics.
Yeah, you run into challenges because you can't measure a photon or usually an electron without capturing it or destroying it. So, that adds another layer. Like, so when you say, well, we measure it and then we let it do the experiment, that's not usually what they mean when they say that. Because if you look at it, you've destroyed it and it can't then do the experiment. So what you have to do is you have to sort of set your experiments up where that it has to be acting in this certain way before it goes into this one spot or something like that. You wind up having to play a lot of tricks to do some of those kinds of things. That's what I mean. So possibly, I'm not sure.
So can this be applied then to the probability? In other words, the description of objects as being a field of probability does not necessarily mean that's the reality. That means that's our knowledge of it is a field of probability, because it may be something more specific than we realize. We just can't measure it outside of a field of probability.
Yeah, well, that's exactly where we're getting into that metaphysical question, or the epistemic and the ontic theories. You're basically saying, there must be some reality underneath that we can't measure, which is one theory. And some other set of people would say, well, that's not clear. We don't know that there's some other theory underneath, and I don't know that we can assume that. And that's another set of theories. And as of right now, there's no data or science that can really conclude either way on that.
Well, I know we all have a lot of other questions, and that's why we have more parts coming up, which is a good thing. Yeah, this is a good discussion. I think it's a good foundational discussion, especially because we've talked about observers, observations, method, and that's all going to become important for the sake of our listeners here in future installments. Again, I'm going to try to steer things, and I can imagine I'm not going to have to try real hard to get into things like, okay, we have this creation event, that's the creationist language, creation event, or the Big Bang, and I realize that those two don't have to be kept separate from each other and all that. But creation event or Big Bang, is that harmed or assisted by quantum physics? That's going to be one thing that we'll probably drift into. The whole issue of entanglement and randomness and determinism. Okay, those are big metaphysical theological deals. Another one would be the spiritual world. Okay, what is that? Like, what's the relationship of the spiritual world to the physical world? Does quantum physics help us understand that? Does it affirm a spiritual world? Does it rule it out? I mean, when we talk about on this podcast, we get into ghosts and demons, and again, these spirit world entity kinds of things. Where are they? I mean, they got to be somewhere, you would think, or is that even the way to talk about it? And then lastly, I'm going to press to conclude the third part with a short list of things that theists and even more particularly Christians should not be saying about quantum physics or can't say. In other words, just help a short list of things to help us guard, not drifting into sort of abusing the field to our own ends and just not really thinking well. So those are the kinds of things that I'm hoping in the next couple of installments we get into. But again, this was a really good foundational discussion. So Putty, thanks for taking your time to do this with us. And I want to thank all the other hosts here for being present. And really, I think everybody had something really insightful to say, and good questions that I'm absolutely positive are going to be in the heads of those who listen to the podcast. So thanks a lot.
It's been fun. I look forward to next time.